We are talking about matter. It's anything that has mass and takes up space. We'll be talking about how mass and weight, they are different, but basically mass, how many atoms are inside or make up the object, and does it take up space. If you put it on your table is taking up space in the room, but also that object like the candle is taking up space on the table. Now, all matter consists of atoms. Atoms have protons, neutrons, and electrons. Protons and neutrons are in the nucleus, while the electrons fly around the nucleus. Now, atoms make up elements. You might have a single atom of sulfur, okay? Or you could have hundreds of atoms of sulfur, but it's still one element. Now, when you have many elements combining together, if we have two elements, such as an oxygen and oxygen, so they are the same, that would be a molecule of oxygen. But molecules can also be different. So you can have a water molecule. So we can have two H's and one O forming a water molecule. So a molecule can be the same element combined or attached together, like O and O, O2, or it can be two different elements, such as two H's and one O combining to make a water molecule. So how's a water molecule, or how's a molecule different from a compound? Well, a molecule is different from a compound because compounds are generally just different elements combining. So if they are the same, it would be a molecule. It would not be a compound. If you have two different elements, it would be either a compound or it could still be a molecule. Okay, it's just a different name for it. It's a little confusing, but don't you love those scientists? Atoms, as we said, they contain three subatomic particles: the proton, which is positive, the electron, which is negative, and the neutron, which has no charge, which is neutral. So the proton and the neutron are in the nucleus, which is in the center of the atom. Elements. Elements are pure substances that are made up of one atom, as we just said, or many atoms, but it's still that single element. So gold can be one atom, or you can have thousands of atoms of gold making a large chunk of gold. Okay, so an element is pure. It's just a single atom, okay, or many of that single atom. It consists of only one type of atom is what I'm trying to say. And elements are listed on the periodic table. Now, you don't have to know the atomic number, atomic weight for right now. You can wait till you go to chemistry. You'll have to be aware of that. Okay. We're also not going to memorize the periodic table, but you do need to know some common elements, and we'll learn about that in the next couple of chapters. Okay, molecules, we said, are a combination. They can either be pure, two of the same, such as O2, two oxygens combining together, or they can be different. Okay, we said H2O, we can have H's and O's are different, so that can be a molecule. Two of the same or two different could be a molecule. But if we go to a compound's very similar to a molecule, but that's just referring to different. As you can see in the examples, we have H and we have Cl combined together to form hydrochloric acid. Those are two different things. You have one H, one Cl, one chlorine, one hydrogen bonded together. They are different. Okay, so there are no similar ones when referring to compounds. Mixtures. Now, as compounds and molecules are going to be combined basically chemically, mixtures are a combination of two or more physically combined, not chemically combined, but physically combined. So I can separate a mixture. I can physically separate a mixture with my hands or through a process. Maybe if I boil water, I'm going from, maybe I have salt water. I'm going to boil water. I'm going to change that water from liquid water to gas water, and I'll be left with the salt. So a mixture is something that can be separated physically with my hands or through the process of maybe evaporation, okay? Because I'm going from liquid water to gas water, it's still water, okay? If something's done chemically, we're changing it into a new substance. So not chemically here for a mixture. Now there are two types of mixtures. There are homogeneous mixtures. The prefix homo means same. The prefix hetero means different. So a homogeneous mixture is a mixture that looks the same throughout. So salt water looks just like pure water, okay, when all that salt is dissolved, okay? That's the key here. All the salt is dissolved, okay? It looks the same. Now, if I took water and I poured salt in it and there's a big pile of salt at the bottom, that would be a heterogeneous mixture because I can see the two separate things. I can see the water, I can see the salt. So that would be hetero. A salad, we have tomatoes, lettuce, cucumbers, carrots. I can see the different things. That would be a heterogeneous mixture. I can pick them out as well.
Water is a homogeneous mixture. I can only identify water in this beaker. I cannot see more than one material or substance. I'm now going to go ahead and add some paper clips to this water. Now, because I can see both the water and the paper clips, this is now a heterogeneous mixture. I can see more than one object. I can see two different things in the beaker, water and paper clips. Therefore, I can see the different things in the water. This beaker contains water and food coloring, two different things, but I can only identify a yellow and orange colored water. So this would still be a homogeneous mixture. I can only identify one thing, even though I know it contains food coloring and water. I can only see one substance. So it looks the same throughout. So this would be a homogeneous mixture. Pencils are in the colored water. Because I can identify more than one object, I can identify the colored water, which look the same throughout, but I can also identify the pencils. So this would be a heterogeneous mixture. I can identify two different things, two or more different things in the water or in the beaker.
Now there are three basic states of matter: solid, liquids, and gas. Solids, liquids, and gas. Now in this unit we're not going to talk about plasma, but plasma is a fourth state, and there are other states, but we're not going to talk about that now. Okay, according to the chart, this is going to be very helpful for you. Solids, the atoms are in very close proximity. They vibrate very, very slow, just a little bit of energy movement here. And then basically solids have a definite shape and a definite volume, meaning a rock will not change shape. You set it on the desk, it keeps its shape, okay? But the atoms in that rock are vibrating, but just too slow for us to see it. It's vibrating. Now, it has a definite volume, okay? So if I drop a rock in water, and let's say I measure that water to be 5 milliliters, then I drop the rock in and the water rises from 5 milliliters to 7 milliliters, that rock would be or have a volume of 2 milliliters. Okay, I went originally no rock in the water, 5 milliliters, just water. Then I drop the rock in, it rises to 7 milliliters, so the rock would have a volume of 2 milliliters. So that rock, that solid, keeps its volume, the space that it takes up. Now, a liquid, though, the atoms are vibrating a little more, so there's a little more energy. Liquids have a definite volume. So if I put 5 milliliters of water in a different shape container, the shape will change, but it still will be 5 milliliters. So let's say I have 12 milliliters of orange juice. I have it in a very thin cup. Well, I pour that thin cup of 10 milliliters, or what did I say? 12 milliliters of orange juice I have 12 milliliters of orange juice into a very wide cup. Well, the shape will change, but it will still be that 12 milliliters. Now, gases, lots more energy. The atoms are moving very fast, very spread out, very far apart. And this is very important when we're talking about molecules in the air. That's why we can walk through it, because these molecules are spread out. So there's no definite volume, no definite shape. I can take a small little container of a gas, let's say a chlorine gas, which is a little yellow, and I put it in a little container, let's say it's 1 milliliter, and then I put it, in a little square container, and I put it in a large round container. Maybe the large round container is 100 milliliters. Well, guess what? The chlorine gas will spread to fill that whole container. So the volume changes and the shape changes. It went from a square to a circle. Okay.